Today we are going to look at the dictionary abstract data type. We are also going to see how binary search is done and what the analysis for binary search is, and then we will go on to hashing, see what is a hash table, how hashing is done, see the collision resolution techniques, and then in the next class we will follow up with more hashing techniques. A dictionary is an abstract data type that stores elements so that they can be located very quickly. So, one example that we can have of a dictionary is we want to store bank accounts, right. Now, when you store bank accounts, what is the key? What is the notion of a key? The notion of a key now is your account number, right. So, a bank account has lots of information associated with it, but you are going to access a bank account or data associated with that account by using the account number. So, the account number becomes your key, and as I said, an account stores a wealth of information, right. It could be your current balance, it could be the name and address of the account holder, it could be a list of transactions that you have done in the last few days, and so on and on, right. But when you have to access any of this information, you need the notion of a key. A dictionary is something that stores the elements. So, the element, when we talk of element, we will mean all this additional information, and when we talk of key, the key would be this account number, which helps us access the particular information. So, any application that wishes to operate an account or to do any kind of an operation on an account will have to provide the account number as a key. Without that, nothing is going to happen. So, it is basically an abstract model of a database. The dictionary is going to store these key element pairs, right. The key could be an account number. It need not be an account number. For instance, in the case of your suppose I had student records, then what would my key be? What would be the most natural notion of a key here? Your entry number, which is not an integer, right. You have characters in your entry number and so on, but anything that uniquely identifies a particular student or a particular account becomes the key. And one of the main operations that is supported is searching by key. What are the kind of methods that we have in a dictionary abstract data type? So, this standard container methods that we have seen for queues and stacks and so on. One is size, which tells us how many elements are there in the dictionary, is empty, whether the dictionary is empty or not, and elements, which returns to us all the elements that are there in the dictionary. Then we will have these query methods, right. So, given a particular key, find the element corresponding to this key. Now, in settings where you might have the same key associated with many different elements, and one could have such kind of settings, we will see examples of this later, then given a particular key, you want to return all elements who have that key. Yeah, you could have update methods. So, given I might want to insert an element E, which has a key k, I might want to insert that into my dictionary. I might want to remove an element with a certain key. I might want to remove all elements which have a key k, right, just what you would think as a standard thing. But now you should remember that there is the notion of a key, and that is crucial for help in searching, right. Without the key, it would be very difficult for us to search through this wealth of data, through this database. We will have a special element nil, which will be returned by an unsuccessful search. What does that mean? That means that if I am searching for a particular key and that key is not there, there is no element with that key in my dictionary, then let us say my procedures would just return a nil, right. This is some special element. Okay. One thing that we will keep in mind is that we only require comparison of keys for equality. So, given two particular keys, we are not going to say one key is less than the other, right, or one key is more than the other. This is not really required, because all you are doing is searching for a certain key. So, all that is required is, given two keys, you want to say whether they are the same or not. There is no notion of ek kisi se bada hai ki nahi, right. So, for instance, again for student records, I could have my key as your name, in which case there is really no notion of taking two names and saying one name is smaller or one name is larger than the other. Right? So, the only operation we will be required is comparing keys for equality, right. So, we do not need any order on our keys really. Okay, how can a dictionary be implemented? So this is the abstract data type, and then what we are going to do in the next few lectures is talk about how this particular abstract data type can be implemented. And we are actually going to see many different ways of implementing this abstract data type. You already have seen some ways of implementing this abstract data type. You could, for instance, use an array, or you can use a linked list to implement a dictionary, right? Can everyone think of how to use a linked list to implement a dictionary? Suppose I had student records, right? How would you use a linked list to implement this dictionary? Every node would have the key, which is the entry number, and all the data associated with that particular entry number, right? It's a very inefficient way of doing things, but it is a way of doing things.
But we said that there is no notion of a predecessor or a successor.
There is no notion of a predecessor or a successor. That is true, yes.
So how would we be connecting those? I mean, on what basis would we be connecting the nodes?
So your question is that if you were using a linked list, how would we organize it? That is up to you. You could connect them in a completely arbitrary manner. You know, the nodes could be in a completely arbitrary manner, or you might want to organize them some way. But you know, you could just throw them arbitrarily into the linked list, and that's fine. That's a linked list implementation. It's not very efficient, but it is an implementation. Yes. Right. So today, what we are going to see is what's called a hash table, and in later classes, we are going to look at binary trees, red-black trees, AVL trees, B trees. These are all mechanisms, data structures to implement just this dictionary abstract data type. It's a very critical, it's a very important data type, and so we are going to be spending quite some time on this particular data type in these lectures. Right, in Java you have two abstract classes. You have an abstract class called java.util.dictionary, which lays out the specification. You also have an interface called java.util.map. Right, you can have a look at what the specifications are for these two classes on your own. Before I get more into dictionaries, so you understand what the abstract data type is, right? Before I get more into it, let's look at the problem of searching. Right? This is a small aside, but you will see why I am making this aside and how it will link up to the subsequent discussions we are going to have. So the problem of searching is the following: you are given a set of sequence of numbers. Let's say these are your keys in a database, anything, and I give you a single number. This is my query. Right? So for example, I could have 2, 5, 4, 10, 7 are the keys in my database, and I query is 5. What do you have to return? You have to return to me what is the position of this key in this database. Where is it sitting? Right? So index of the found number or null or nil. Right? So 5 is sitting at position 2, so you return 2. While here 9 does not appear anywhere here, so you return nil, saying it does not appear.
So your first homework, you have to suppose that you know the universe of your keys beforehand. That is all the keys that can come for insertion or search. Okay, so let the size of this universe be R. Example, for a 20-bit key, you will have R 2 to the power 20, which is a very large number. The first question is, can you solve this search problem that is specified here? Okay, so you have to search for a particular key, and can you do it using an array at order 1 time complexity, and what is the space complexity of this solution? And if your actual number of keys which are coming to be inserted, your universe might be very large, but the actual number of keys which are coming might be n, and n might be much less than your universe R. So can you solve the same search problem at order n space complexity with some data structure, and also comment on what will be the associated time complexity of search in that case?